Stars in the outer regions of galaxies are moving in ways that no known force can fully account for. A galaxy is not a static structure. It is a system in constant motion, billions of stars orbiting a common gravitational center, their paths shaped by the mass distributed across the system. Under the physics governing this motion, stars closer to the galactic core orbit faster. Stars in the outer regions, where mass becomes sparse, should orbit more slowly. The relationship between mass and orbital velocity is not speculative. It is derived from the same gravitational mechanics that predict planetary motion, tidal forces, and the behavior of every large-scale structure physicists have tested across centuries of observation. It holds for moons around planets, for planets around stars, for stars in dense clusters. There was no known reason to expect it to fail at galactic scales. A galaxy's visible mass, its stars, its gas clouds, its dust, was treated as the primary driver of stellar motion. Measure the light, estimate the mass behind it, apply the equations, and the orbital velocities at any radius should follow directly. The prediction was not ambiguous. It was a specific, testable number at every distance from the galactic center. The observations did not match. Beginning in the 1970s, systematic measurements of galactic rotation revealed a pattern that violated this expectation across hundreds of different galaxies. Stars in the outer regions of spiral galaxies were not slowing down as the equations predicted. They were orbiting at roughly the same velocity as stars much closer to the galactic center, or in some cases, slightly faster. The rotation curves, plotted as velocity against radius, were flat when they should have been declining steeply. This was not a marginal discrepancy. Across surveys conducted independently, using different instruments on different galaxy types, in different parts of the sky, the pattern repeated. Something was wrong. Either the gravitational equations failed at galactic scales, or a large quantity of mass existed in these galaxies that no observation had ever detected. The standard explanation introduced to resolve this discrepancy is dark matter, an undetected form of mass distributed in extended halos surrounding visible galaxies. If additional mass exists beyond what can be seen, concentrated in a roughly spherical envelope around the visible disk, it could provide the extra gravitational pull needed to sustain the observed velocities at large radii. The dark matter halo model has been incorporated into the standard cosmological framework and is used in virtually all large-scale galaxy formation simulations. It is not a marginal idea. It is the working assumption of most astrophysical modeling conducted in the last 50 years. But the nature of dark matter remains unknown. No particle has been detected that matches its predicted properties, despite decades of direct detection experiments operating deep underground, shielded from cosmic ray background, sensitive to the faintest possible nuclear recoil signals. Multiple experiments, LUX, Xenon, 1T, Pandax, and others, have systematically excluded large regions of the predicted parameter space without a confirmed detection. No electromagnetic signature in any wavelength has been confirmed as dark matter emission. The halo exists in models as a mathematical necessity derived from orbital mechanics, not as a confirmed physical entity with measured properties. Something is pulling stars off the paths that visible mass alone would set. That something has never been directly observed. Within the framework of dark matter halos, a further question emerges. What is the internal structure of the halo itself? The original model assumes a relatively smooth, spherically distributed mass. Stars orbit within a gravitational well shaped by this smooth envelope, and the flat rotation curve emerges naturally from the additional mass at large radii. The model works when applied to the aggregate motion of all stars at a given radius. The problem is that galaxies are not featureless. Individual stellar populations, stellar streams, and kinematic substructures show velocity patterns that a perfectly smooth halo does not predict. Stellar velocity anomalies within individual galaxies are not uniformly distributed. Some regions show larger offsets than smooth halo models produce. Some show offsets in directions inconsistent with the expected pull of a symmetric halo. Stellar streams, Long arcs of stars stripped from smaller satellite galaxies and distributed across the galactic plane over billions of years show velocity deviations that do not follow simple gravitational trajectories, even when the satellite's known mass is fully accounted for. Something additional is acting on them. These irregularities have led some researchers to propose a more structured dark matter distribution. Rather than a featureless halo, dark matter may organize into streams or filaments, coherent directional flows of material moving through the galactic system. If such structures exist, their gravitational influence would not be uniform across the disk. Stars passing near a stream would experience a localized, asymmetric pull that smooth halo models do not include. The velocity offsets would appear irregular, not following a clean radial pattern, not predictable from the visible mass distribution, and not consistent with a single smooth halo fit. They would look, from the outside, like something invisible was selectively pulling specific groups of stars off their expected trajectories. No such stream has been directly detected. Every piece of evidence proposed in support of this structure is derived from the anomalies it is invoked to explain. The stream is inferred from its effect. The effect, however, must first be distinguished from every other known perturbation source before it can reliably be attributed to anything at all. This is the structural problem at the center of the evidence gap. Measuring a gravitational effect requires knowing what produced it. When the source is invisible, undetectable, and structurally uncertain, the measurement cannot confirm the source. It can only confirm that something produced a net force. The stellar velocity offsets are real. They have been reproduced across multiple independent surveys using different instrumentation and different analysis methods. What caused them, what geometry, what mass profile, what trajectory, cannot be read directly from the data. Attempts to constrain dark matter structure through stellar kinematics face a limitation that precision alone cannot overcome. To infer the shape and density of a dark matter distribution from stellar motion, the full orbital history of those stars must be reconstructed. Stellar orbits are not simple paths. Over billions of years, they accumulate perturbations from encounters with molecular clouds, from the density waves propagating through spiral arms, from the gravitational influence of satellite galaxies passing at various distances and angles, and from the long-term tidal residuals of galactic mergers that may have occurred billions of years ago and left dynamical signatures persisting into the present. None of these perturbation histories are directly observable. They must be modeled. The uncertainty compounds with each assumption. Every additional perturbation source introduces noise into the inferred dark matter distribution. A velocity offset that appears to indicate a localized dark matter stream may partly reflect the tidal influence of a recent minor merger. A region that appears consistent with smooth halo predictions may contain substructure below the current detection threshold. The more precisely researchers attempt to reconstruct the dark matter distribution, the more sources of uncertainty they must account for, and the more opportunities exist for those uncertainties to produce patterns that resemble, but do not confirm, a directional dark matter flow. More data has sharpened the anomaly without resolving it. The Gaia mission has cataloged the positions and velocities of over 1 billion stars in and around the Milky Way with precision unachievable a decade ago. Analysis of this dataset has identified coherent stellar streams, velocity substructures, and dynamical features that previous surveys could not resolve. Several of these features show properties consistent with perturbation by a localized gravitational source that does not correspond to any visible structure in the galaxy. Some have been tentatively linked to the predicted passage of dark matter subhalos, concentrations of dark matter smaller than the main halo, orbiting within it on their own trajectories. The Sagittarius stream, a long stellar arc torn from a satellite galaxy, shows velocity irregularities that some analyses attribute to encounters with dark matter substructure along its path. The Monoceros ring, a stellar overdensity in the outer disk of the Milky Way, has a velocity profile that resists clean explanation under smooth halo predictions. The Hercules stream, a kinematic grouping identified in Gaia data, carries velocity patterns that have prompted proposals of perturbation by an unseen mass concentration. These are patterns consistent with the stream hypothesis. They are also consistent with alternative explanations that have not been eliminated. Higher resolution data has revealed more irregularity in the velocity distribution, not less. The structure of stellar motion across the Milky Way is more complex than early dark matter models anticipated. Whether this complexity reflects genuine substructure in the dark matter component or residual dynamical effects from the galaxy's merger history that current models do not fully capture, or some combination, or something else entirely, cannot currently be determined from the data in hand. Measurement error in this context is not a simple calibration problem. Spectroscopic velocity measurements of individual stars have improved substantially. But precision in measuring stellar positions and velocities does not translate directly into precision in inferring the distribution of a mass component that cannot itself be measured. The gap between what is observed and what is inferred grows with the structural complexity of the hypothetical source. A smooth halo requires minimal assumptions. A filamentary or streaming distribution requires modeling the stream's trajectory, its mass density profile, its velocity relative to the disk, and its interaction history with visible matter, all of which are unconstrained by direct observation. Dark matter streams, if they exist, cannot currently be confirmed or falsified. They produce velocity effects that are consistent with observations. So do alternative dark matter configurations. So do certain modifications to the gravitational equations at low acceleration, theories that do not invoke unseen mass at all, though these face difficulties in cluster dynamics where dark matter models perform better. No single observation available today discriminates cleanly between these possibilities. One partial result has emerged. The total mass enclosed within the Milky Way's dark matter halo has been constrained within a range, derived from the aggregate motion of stars and satellite galaxies across a wide range of distances. The halo exists as a mass component with statistical confidence. Its total mass, within substantial uncertainties, has been bounded. Its internal structure, whether smooth or clumped, whether organized into directional flows, whether those flows have measurable asymmetric effects on stellar populations in specific regions of the disk, has not been determined. That question requires distinguishing a dark matter signal from the accumulated dynamical history of the galaxy using observations of objects whose past trajectories can only be estimated in a system where the dominant mass component produces no detectable signal of its own. Stars continue to deviate from their predicted paths. The structure of what is pulling them remains uncharacterized. The force has a confirmed aggregate effect and no confirmed geometry.